So does it show anywhere that it has started? I just started it. Yeah, I think it is. Oh, yeah, it is recording. Fine. Okay. All right. Then maybe I will just I'll just go through what I said before. Yeah. Okay. So what I was saying is, yeah, what I was saying is that these, if you look at, these. So what he said is that this one is a very important thing that you should remember. A fundamental product. A fundamental product, or often we just call it a product. Okay. Fundamental product, or sorry, fundamental product, or for short you can just call it a product. It's often called a product term. I mean, people usually don't use the term fundamental product. That's a more formal term. This is the terms that are more commonly used is a product term or a cube. Okay, these two terms are commonly used. So if you will normally not hear the term, I mean hardly anyone uses the term fundamental product. It is a fundamental product. It's a formal term. It's not used in practice. In practice, you use a fundamental product is just called a product, or it is also called a cube. All right. We'll see why it is called a cube. I mean, there is a very obvious geometrical reason for calling it a cube. We'll see that pretty soon. But the important thing is, so a fundamental product involving all the variables. This is important. All the variables. All the variables is called a mean term. This is a very important. And you can see that these are the mean terms. So if you have two variables, so you can see that you have these are the fundamental products involving all the variables. All right, involving all the variables. These are not fundamental products, by the way. I mean, this individually, this is a product, this is a fundamental product, but this whole thing is not a fundamental product. That is a sum of product expression, because this one is a product. Let us say this one is a product, and this one is a product, and these two together. So I don't want to. Right. This one is a product. This one is a product, and this whole thing is a sum of products. But this is a mean term, and as you can see, that these mean terms appear as the atoms. These appear as the atoms of the lattice. And what you remember is that any element of the lattice, so these nodes that you see, or let me just put it in a different, these nodes that you see, these are really the elements of the lattice. Okay, these are all elements of the lattice. And if you recall that when he talked about the representation, that each node has a irreducible, irredundant sum representation of the atoms of the lattice, right? You have an irredundant, irreducible sum representation. So that is exactly what you're seeing. That is, every element of the lattice, that means all of these actually, all this circle, these are elements of the lattice, and they have this is so yeah, they have, let me just every what I saw is that every element of Boolean lattice has oh, that is one thing, and the other thing is this sum is unique up to permutation. That is very important. It is unique up to permutation. So what you have seen is that you can, we have already, you have already seen in the lab, and we have also mentioned it, a Boolean function can have several representations, and that you have already seen. We have already, uh, shown that in the class, and I think you're a Boolean function can have several representations, but this is the important point, that the representation in terms of this atoms, and these atoms, as you have seen, these are nothing but the mean terms. And what are these mean terms? Mean terms are fundamental products with or having all the variables. Fundamental products having all the variables. So that is what these mean terms are. And so if you look at this, a Boolean function can have several representations, but the representation in terms of its mean terms is unique. Alright, the representation in terms of its mean terms is unique. So such a representation is also called such a representation is also called a canonical sum. Is called SOP, that maybe I can just write canonical sum. All right. So, do you get this? This is a very important point to note. This is called a canonical sum of product representation. This is a canonical sum of product representation. Yeah, so is this clear to you, all of you?
Yes,
Yeah?
sir.
Okay. Now
Yes,
let me
sir.
ask you one question. Do you think it's a good idea to represent a Boolean function using its canonical sum of product representation? One advantage, of course, is that the representation is unique. That is an advantage. So is it? So I'm asking you this question. So just think and reply. Is it a good idea to represent a Boolean function as its canonical as a canonical sum of products? What is your opinion? Yeah, just think and tell me. What do you think? Is it a good idea to do that? Yeah, good or not good? What is your opinion? Just think and tell me. Say something. Just whatever you think, you tell me. I can't see your writing in case you're writing. So just tell me. Yeah? This is actually an important question. Are you able to answer? Do you have any? Okay, I take it that you can't answer as yet because no one has answered. So let me ask you another question. Look at this lattice. Look at this lattice and give me the canonical sum of representation of this element which I have marked. What is the canonical representation of this element which I have marked, which I'm pointing out to this element? Give me what will be the canonical sum of
AB plus AB bar plus A bar B plus AB whole bar.
Yes, that is true. But what is the Boolean function? So how do you, so now it is simple. You just, so your Boolean function, what is your Boolean function is 1. Okay, and your SOP representation is, isn't it? So how do you compare the two? This is much bigger, right? Yes or no?
Yes.
This is much bigger. So that is the problem. So your canonical, I'm just calling it CSOP. CSOP, the size is maybe exponential, maybe just put it this way. Maybe exponential. In the number of variables, right? Maybe exponential in the number of variables. Of course, in this, so this is the problem with your canonical sum of product representation. It is unique, that is the good thing about it. But a serious problem is that it may be exponential in the number of variables. So a variable or its complement, these are called literals. This is literals. All right. So these are some common, terms that you should know. So literals, cubes, products. You should. Otherwise, you'll not be able to follow when people talk about these things. So yeah. So this is all right. And as I told you, just so each variable, so the role of each variable is nicely depicted in this Venn diagram. So if you have, so for this situation, for this Boolean lattice with 4 atoms, uh, with 4 atoms, can you draw the corresponding Venn diagram? Yes. This Boolean
Yes, sir.
lattice. So how many? Yeah, I mean, okay, it is actually a very simple question, but just to be sure, So it will be, so if you go by this, it is A, this is B, and if you go by, that numbering, you have 1, 2, 3, and 4. These are the 4 regions with a, alright. So can you write down the mean terms for these 4 regions? I think that is the most interesting exercise. Can you write down the mean terms? So you can tell me what is the mean term for 1?
AB.
Huh?
AB.
Okay, good. So let us just write AB. For 2,
A B bar.
A B bar.
Yeah, that's right. For 3,
A bar B.
okay. And this one, I think you can still
A
tell.
bar, B bar.
Okay, so now you understand this. This is, I mean, it's a simple exercise, but it's also an instructive exercise. All right. So you can, so what you can say is that, you know, I mean, you have, we have studied it mathematically in terms of lattices, but if you more intuitively, I mean, if you look at this Venn diagrams, what you can say is that any, you know, any combination, any situation can be expressed in terms of these regions, right? Any situation can be expressed in terms of this region, and that is exactly what this lattice does. It just says that, you know, in any situation. So 0 indicates that, you know, you don't have any of these situations, and 1 indicates that you have got all of these situations, and all these intermediate nodes represent various combinations of these situations. I mean, if you interpret it that way, that is just what it is. Okay, if you interpret it that way, that is what it is, and the lattice simply tells you the coverage. So, you know, a node like B, it simply says that it involves both AB and A bar B. Okay, if you look at it in terms of the base situation, so this node, it covers both these situations. That is, you know, so you have a very, I mean, it is not so esoteric also. I mean, we have studied it mathematically, but if you look at it, you know, intuitively, it is really very straightforward. It just depicts various situations. All right. So these Boolean functions just represent various combinations of this base situations. That's all. And uh, yeah, all right, okay. So that is a more, you know, intuitive understanding of this Boolean functions. Okay, so let us carry on with this. All right. So you have looked at, we have already studied this functional completeness. So yeah, so I mean, you have to be a bit careful regarding this functional completeness. So actually, this functional completeness, it is NAND. Okay, so how do you get AND from NAND? So for example, you have, so NAND gives you XY bar. All right. So if you want to get, so you know that, okay, so from this, if you want to get, say, X bar, how will you get X bar? How will you get X bar from using a NAND gate? Can you tell me? How will you get X bar? I mean, you know it, I'm just asking you.
You connect both inputs to X.
You connect, or you can rather say this way, uh, yeah, so you can, yeah, that is one way of saying that you connect both inputs to X. That is one way of saying. So you could, yeah, so this is one way of saying that this will give you x bar, and of course if you do this, this will also give you x bar. This will also give you x bar. But that is an important observation. It just, yeah. So yeah, so you could say that NAND by itself is functionally complete. Actually, yeah, I was just thinking that maybe you require, yeah, NAND and 1. NAND and 1. This is, I mean, you would require, so here actually you are using NAND and 1 to compute X bar. But as here, as you can see, you are able to compute X bar. You don't need the 1. You are computing X bar just with X. So, yeah, so that probably suggests that NAND by itself is enough. Is enough to get, yeah. Yeah, so as you can see, using NAND you can compute AND. So if you want to compute, you know, X and Y, so one way of doing it is you can use a NAND gate. You compute NAND and then you do this and you do this, so this will give you XY. And then of course you can use De Morgan's laws to, you know, get, this gives you naught. Sorry, I just made a mistake. This will give you XY, not XY bar. This will give you XY. Yeah, and then using De Morgan's laws you can get OR as well. So yeah, so from that point of view, it looks like NAND itself is functionally complete. You probably don't need that 1 because you are able to compute. You are able to, you know, compute all the functions using just the NAND gate, even without using this 1. So that's actually an important observation. What you so this is it's a non-trivial observation. All right. Yeah. So here you have, I mean, by the same argument, you could, I think, say that you can obtain this thing. NOR by itself is also functionally complete. XOR AND. So XOR AND is another combination of Boolean functions that is functionally complete. This one, so RAM, up to RAM I have covered. This minority function, this I leave to you as an exercise, okay? This I leave to you as an exercise. So I shall leave it to you to establish that the minority function. So this is an exercise. Of course, we will put it in the we'll put it in the assignments that you'll have to do. So you consider two functions, the minority function and also the majority function. And consider their functional completeness. This I am giving to you as an exercise. So it will be there in your exercise sheets, but I'm just giving, I'm just spelling it now in the class, okay? Oh, by the way, another important announcement is that next Wednesday, I think that is February 10th, right? Next Wednesday, that is February 10th. Yeah, so this is, please, I'll also put it on WBCN. This is CT2 on February 10, 21, and topics is everything So this is your announcement for class test 2. Please make a note of it. I'll put it up on WBCM also. Yeah, but do make a note of it. Okay. Yeah, so this is your this is your exercise on minority and majority functions. Okay, so these are various Boolean expressions. Okay, these are various Boolean expressions. So I've just given examples of various Boolean expressions. So a SOP expression, a sum of product expression, where each functional product is a mean term, is called a disjunctive normal form. That happens to be. It's also called a canonical sum of products. It's also called the disjunctive normal form. Okay, it's called the disjunctive normal form. And as we have already seen that it is a unique representation. So when the representation is unique, it is called a canonical representation. So this term which you see here, canonical representation, this canonical is associated with uniqueness. It is associated with uniqueness. All right. Okay. So that is your canonical. So now if you so this these are called, you have this mean terms, and you also have max terms. So an element like x, is that is a max term. Okay. An element x is in a Boolean lattice is a max term if it if it has 1 as its only successor. This is just a little, I think it is better not to write that x, because x is not a variable. So actually these are your max terms. These are your max terms. Okay, and as you have seen, what you have here, these are your mean terms. So mean terms are your atoms. So mean terms have 0 as their predecessor. Okay, and max terms have 1 as the successor. All right. So yeah, so that's That's a max term. And so a max term is a sum of literals involving all the variables, as you have seen. This mean term is a product involving all the variables, and this is a sum. A max term is a sum involving all the variables. So that is what a max term is. Yeah. Now, similar to a sum of products, we have already seen what is meant by a sum of products. So similar to a sum of products, you can also think of a product of sums. So here, I mean, if you look at this lattice, this is a very symmetric structure. Okay, this is a very symmetric structure. So if you can go from the atoms upwards using join. Okay, using join, or if you call it a sum, this is, and similarly, the same thing you can do, you can come down also. Just as you can go up, you have seen that from bottom to top, you can go up, and I mean that's what you saw. You have each element can be represented as as a irredundant, irreducible sum. So you can also go down because it's a symmetrical structure. If you look at the structure, it is completely symmetrical. So you can also go down, and when you go down, you're using the meet operation. And as you would expect, just as you can have each element can be represented as an irredundant, irreducible sum of the atoms, or you can say the mean terms. You would expect that just the dual of that. That means each element of the Boolean lattice you should be able to represent as the irredundant, irreducible product of the max terms. So that is called the principle of duality. Let me just write over here. Principle of duality. All right. So you can interchange. You can interchange these operators, and so any theorem in Boolean algebra has a dual which you can obtain by interchanging the operations. And the reason for that, as you can see, it is just the symmetry of the lattice. Just as you can go from bottom to top using the join operation, you can do exactly the same thing. You can go from top to bottom using the meet operation. Okay, so that's why you have this. That is the you can say the geometric reason, or that is the basic underlying reason behind the principle of duality. All right. Okay. So correspondingly, just as you have a disjunctive normal form, okay, disjunctive normal form, the sum of products, the product of sums, when each sum is a max term, then you have another representation which is called the conjunctive normal form. So note that and this is also a canonical representation. Canonical meaning a unique representation. So just as you have the disjunctive normal form as a canonical representation, you can also have the conjunctive normal form. So disjunction means it's a sum and conjunction means product. So you have sum of products and products of sum, and when you consider sum of mean terms, that gives you a disjunctive normal form, and when you have a product of max terms, that gives you another another canonical representation, which is the conjunctive normal form. All right, which is the conjunctive normal form. All right, and now you can it is easy for you to see why the POS will that is the canonical product of sum. Why the canonical product of sum will be unique, and its uniqueness simply follows through the principle of duality. Okay, you can of course prove it all the way. I mean, just as we did for the irreducible irredundant sum, just as we developed the theory based on the properties of a lattice. We came up with the irredundant irreducible sum. So you can it's possible to do the whole thing with the max terms and use the join operation instead of use the meet operation instead of the join operation, or very simply you can just use the principle of duality, because the lattice is a fully symmetric structure. So the principle of duality is very important. So if you have one theorem, its dual is also a theorem, all right, in Boolean algebra. Okay, so I think we can stop here today. I mean, we have done most of it. We'll just complete this on Monday, and I'll put up the slides also. All right, so we'll stop here today. Yeah.